So Kevin just talked about how a single CPU is already a distributed system and all the challenges involved in getting high performance on just a single CPU, a single socket. And unfortunately, these challenges don't get any easier when you go from the distributed system inside a core or inside a box to the distributed system around the world. I'm Philip Taffet. I'm one of the core engineers on FireDancer. And I'm going to talk about some of the work we've done accelerating Reed-Solomon for fast network communications. So the core of the problem, to use a phrase that our team likes to throw around, is that networks aren't magic. We have this goal that we need to distribute new transactions that are landing on chain around the whole world. Across the whole, the world is big. And so you might think about several ways to solve this problem. One is, okay, maybe there's some Ethernet broadcast and you can just have the network do it. Well, no, that doesn't work. It might work on a local network, but in reality, the internet is point to point. So you can't just have the network magically broadcast your packet. Okay, well then you could try solving this by saying have the core of the distribution send this information to each recipient. That solves the point-to-point issue. But no, that doesn't work either because real networks have finite bandwidth. And if you are sending each packet multiple, this basically doesn't scale. If you're sending each packet tons and tons of times, you're cutting your bandwidth by a huge factor. All right, well then we can solve the bandwidth problem by, say, distributing it in a ring, where you send the packet to the first recipient, they forward it along, and that does solve the bandwidth problem, but no, this is not a good idea either because real networks have non-trivial latency. So, each of these links might be halfway around the world, and by the time you add up a bunch of these, you try to scale this idea, you might as well be sending a postcard. Okay, so then idea 4. We're running out of ideas here, but how about we distribute it in a tree? So if you think about the last two ideas, the ring and the all-to-all, they're both kind of extremes of the tree. So all-to-all is a tree with very high radix, and ring is a tree with very low radix. But we can take this as a dial and dial the radix of, you send a packet to one recipient, and they forward it to just a few recipients. And this lets us trade off the balance between latency and bandwidth. Well, still no. Getting closer. But the problem with this idea is that real networks are lossy. And of course, this problem affects all the ideas we just talked about, but it is particularly insidious for this one. Let's take a look at why. So say we lose this packet between L and A. Well then, it's not just A that doesn't get the data, it's A and anything that A would have sent it to, which means this whole, potentially the whole large portion of the network isn't getting this packet. Okay, so then how about we solve this problem by sending it in a tree, but also sending some redundant information, some parity information. And here we go. This is the way that we'll solve it. So that motivates our need in order to get a working, high-performance distributed global broadcast. We need some kind of parity information, some kind of redundancy information, so that we can recover when packets get lost. There are many ways to do this. Reed-Solomon is one way, and that's the way we'll focus on now. So I'll dive into Reed-Solomon and explain first, the background, how it works, and then how we implement it in a high-performance way. Okay, so to start with explaining Reed-Solomon, we need to start with just a very basic fact that you might remember from grade school, and that's that 2 points define a line. So say we have 2 points, I'm standing in the middle, in the way, 2 and 3. Well then, there's only one line that goes through them. It's this line that I've shown in green. And there's no choice. We can't wiggle the line. We can't shove it around. It has to be that line. And that's true for any pair of numbers. So say 5 and 5, 4 and 0. Any pair of numbers like that define exactly one line. And we can use this line to define some more points just by taking the y value at subsequent x coordinates. So say, what is that, 4, 5, and 6? And so the cool part is that we can use any 2 of those points, we had 5 points, any 2 of those points define the exact same line. So if we start with the first and the last instead of starting with the first 2, we get back the same line, and then we can use the same line to regenerate the points in the middle. And we get back the same 5 points that we got when we started with the leftmost 2. That's it. That's the core idea behind Reed-Solomon encoding. So if we want to send the byte 2 and the byte 3, then we build the, we construct this line, and we also send redundant information, say 4 and 5. And we send these each in different packets so that as long as the recipient has received 2 of these packets, they can reconstruct the line and reconstruct 2 and 3, which are the values that they actually cared about. Of course, they might want to send, or we might want to send more than just two values. But this, 2 points define a line has a very simple extension, which is that in points define an order n-1 polynomial. So if we wanted to send 3 points, say 4, 1, and 2, we just build a quadratic instead. If we wanted to send 4 or 3, we'd build a cubic. 3 makes a quadratic, 4 a cubic, and so on. So if we wanted to send 4, 1, and 2, then the additional parity information we'd send in this case is 7. You might start to notice a problem though. So here, 7's not that big, but this quadratic is growing pretty fast. So the next point, if we wanted to send 2 parity points, would be 16, then 29. And these numbers are growing kind of fast, quadratically to be precise. And if, this is just an order 2 polynomial. Imagine we had an order 32 polynomial, which is what we actually want. These numbers are going to grow super fast. So here we harken back to what Kevin just talked about. You didn't think you'd be hearing about finite fields so soon again. So we're back to Galois fields for dummies. And the key thing is that they don't blow up. That this fact of in points define an order n-1 polynomial is still true in a finite field. I'm going to keep showing these polynomials as if they're ordinary, your garden run-of-the-mill polynomials over real numbers. But the key thing to know is that we have this blowing up issue under control. Okay, so far everything I've talked about you could probably find on Wikipedia, maybe on the GeoCities website. Just a basic explanation of Reed-Solomon encoding. But now let's get into how we actually calculate this. First, from a theoretical perspective, and then from a computational perspective. Okay, so back to our friendly line where we have the values 2 and 3, and we want to find what y2 and y3 are. So I mean, your first thought of, or at least my first thought of how I would do this is, going back to what I learned in high school. We have the parent function for any line, y equals ax plus b, where a is the slope and b is the intercept. And we have some values of x and some values of y, and we want this line to pass through. So we set up a system of equations, and we solve it for a, and we solve it for b. And we get, a is 1 and b is 2, and then we have some x values where we want to evaluate it. So we plug in our a and b that we just computed, and we get our new y values. All right, so this works, but it's very slow. Because solving the system equations, probably you do it with like Gaussian elimination or something, and it's O of n cubed, where n is the number of data points we want to, or the size of our system of equations here. Okay, that's, O of n cubed is slow, and if our process of computing parity information is, slow compared to the process of, say, retransmitting, this whole idea falls apart. So we need to make this much faster. So the key insight in making it faster is that we actually don't care at all about the values of a and b. We only needed them as sort of an instrument to compute the parity points that we cared about. But if we had some technique where we could compute the parity points we cared about without computing a and b, that would be just fine. So we use a technique called Lagrange polynomials. So this is a special set of functions that have well known, they take value 1 at one of the points we care about and 0 at all the other points we care about. So here they're lines because we're working with lines. So L0 is a line which takes value 1 at 0 and value 0 at all the other points we care about. In this case, it's just 1. And we take this line and we scale it by 2 because we're looking for a line that has 2 at 0. And of course, 2 times 0 is still 0, so that part doesn't stay. Okay, let's leave that line there and move on to L1, the second Lagrange polynomial for lines. So again, this one, it takes value 0 at 0 and value 1 at 1. And we scale this one by 3, again, because we're looking for a line that has value 3 at 1. Okay, and then we take these two and we add them up. So I'm going to temporarily shade the region under so you can see the addition. So we add them up, and what do you know? We get the line that we care about. So another way of expressing this line, earlier we had the y equals ax plus b format. Another way of expressing it is 2 times L0 plus 3 times L1, where 2 and 3 are the actual data points that we were interested in sending. Okay, so how does this help at all? Well, the nice thing is that these Lagrange polynomials are well known. These are something that you can find in a textbook, something you can write down. And so you can compute them, these pre-computed tables of their values at any point you might care about, way ahead of time. You don't have to do this at runtime. Which means that you can compute y at these points by, say, taking the first column and multiplying it by 2, and the second column and multiplying it by 3, and then you add those up and you get your y values that you wanted to send. So again, the 2 points on top are the data points, and then the parity points on the bottom. So I've placed all these numbers very suggestively because this process that I just showed is actually just a matrix vector product. You have this hard-coded matrix determined by the Lagrange polynomials, something you could find in a textbook or pre-compute, and then you multiply it by the data you want to send, and you get the data you want to send followed by the parity points that you need to send so that the recipient can reconstruct missing packets. And the cool thing is that this same process works. I was just showing it with lines, but it works even with higher order polynomials. So this is a linear operator. You might think it only works with lines, but actually the Lagrange polynomials kind of encapsulate all the nonlinearity or the higher orderness. So when you have, say, an order 10 or order 30 polynomial, it still becomes just a matrix vector product. Okay, so how does this do? Well, it's O of n times n, where n is the number of data points and m is the number of parity points. And it's okay. It's a lot better than O of n cubed. So we're making progress. But is this where we want to stop? Well, no. We can go faster. So if you look at this matrix, building off this idea, if you look at the matrix that we were actually sending in the finite field that we're working with, 2 to the power 8, for, say, this is 16 entries, you can see, at first glance, it might look like a bunch of random numbers, but I've colored it, and hopefully you can see the patterns. This matrix is actually super structured. So you have the top left quadrant and the bottom right quadrant, and they're actually identical. Same with the top right and the bottom left. And this pattern repeats recursively. So within the top left quadrant, the top left subquadrant and the bottom right subquadrant of the top left quadrant are the same. And actually, this whole matrix is defined entirely by the first row, the numbers in the first row or first column, and then this recursive pattern. So you just apply it recursively, and you build the whole matrix out of that one row. And in this kind of math, typically structured in the matrix, means that there's a faster way to multiply by it. Maybe it means you can represent it sparsely, or you can represent it as a product of sparse matrices, or something like that. And so after seeing that this was the matrix, I started digging around on the internet to see what I could find of thinking there's surely a faster way to multiply by this matrix. And I actually found a relatively recent paper from 2016 about using a FFT-like approach, that's fast Fourier transform-like approach, for multiplying by this matrix. So this is Reed-Solomon encoding has been around since I think the 40s. So really old technique, and 2016, really relatively speaking, a really new paper. And this paper gives an in-log-in approach for multiplying by that matrix. We'll go into a little bit of the details, but if you've seen any FFTs, you know that they're built out of these butterfly operators, and you get pictures that look like this. So here, they're slightly different, compared to a normal FFT, but this is the core idea inside the paper. Basically, is encapsulated in these two pictures. All right, so that with the ideas in this paper, we get a very fast theoretical approach in log-in for computing Reed-Solomon encoding. Now we have to take a look at how we can actually compute this on real hardware. All right, let's expand a little bit on one of these diagrams. So you might notice the diagram looked like a lot of combinations of this, and the details are not terribly important. But what this diagram means, and broadly speaking, the whole bigger diagram, is that you take some input value and you multiply it by a constant, and then you add it to another input value, and then you add it to another input value, and that gives you 2 output values. And you do this recursively, which means that the entire computation of Reed-Solomon encoding can be done by just multiplication by constants and additions. Which is great, because those are, this complicated operation boils down to a bunch of really simple operations, and all the details are in, which constants you multiply by, which things you multiply those constants by, and the exact order in which you add them. All right, but now we got to go back to Kevin's slide, and remember that we're actually working in a finite field and not just, normal integers or normal real numbers. And we go back to specifically this line at the bottom. Galois fields use weird addition and multiplication tables. And here, this is a different finite field than Kevin was working in, much, much smaller. but even in some senses weirder. So addition is not addition mod something like you would expect for a prime field. It's actually just binary XOR, which is nice because this is a primitive built into every single programming language, something CPUs can do very well. But on the other hand, multiplication is not multiplication mod something. There's no easy way to describe it. It's what Kevin was talking about, irreducible polynomials and so on. Thankfully, this finite field is common enough that CPUs actually give you have multiple instructions, or newer CPUs have instructions for computing it. So here we have the cat walked across the keyboard, as Kevin calls it, VGF2P8 affine QB. So this instruction, if you read the description of it, doesn't really seem to have much to do with finite fields at all, except for the GF2P8, is kind of suggestive. But if you look at it a little bit sideways and squint, you can see that this actually can be used for Galois field multiplication, in this finite field, but only really when you're multiplying by constants, because you have to formulate one of the arguments in a very esoteric format. And if you had to compute that at runtime, you would lose all the benefits you get of multiplying it by. But thankfully, you might remember from the previous slide, all we want to do is multiply by constants. So this is perfect for us. And then, this gives us an implementation of the two little primitives, but now we still have this problem of how do we, make sure we're multiplying by the right constants, how do we make sure we're multiplying the right things and adding the right things at all time. So we take a page from the normal FFT literature and use a technique that people have been using to accelerate fast Fourier transforms for years, and people have put a lot of effort into this. And that's one of auto-generated codelets. So this is where you take you make all these you pre-compute a piece of straight line C code, so no branches, no if statements, and you make all the decisions that you need at computation of the codelet time. So this is where you decide which things you're going to multiply by, which constants you'll multiply by, and you put those make all those decisions way ahead of time, so that when the CPU gets the code that it needs to execute, all those decisions have been made. The constant just appears as like a literal in the assembly code, and the CPU can run through this code blazing fast. All right, so what do we get when we put all these techniques together? Well, a very fast Reed-Solomon encoding library and decoding library. So we get, this is just some Ice Lake machine that I do some development work on. I benchmarked it quickly, I don't know, yesterday or the day before. And I was getting 120 gigabits per second for one core for Reed-Solomon encoding, and 50 gigabits per second for decoding. And this is our common case that we've optimized most heavily. And if you compare that to the Rust crate that does similar work, that's used by many projects, we're 14 times faster, basically. All right, so wrapping up, I think it's pretty easy to summarize this. We take the fastest theoretical approach that's known in the literature, this in-log-in FFT-like approach, and we combine it with some of the fastest implementation approaches at the low-level nitty-gritty, and we get a blazing fast Reed-Solomon library, which means that when we need to transmit data to broadcast it worldwide, we have a fast, low-latency, reliable global broadcast for Fired Answer. All right, thanks, and I'll be happy to take questions.